Would you trust a computer to make a decision about your future, even if it's 99% accurate? Algorithms are already able to determine if you qualify for a loan, your resume will get looked at first, or even help with screening for a medical condition. But if it's not built correctly or their outputs aren't reviewed by a human, it could be completely wrong. The secret is that the algorithm doesn't actually know what a good decision is, just what past outcomes have looked like. And if those patterns are flawed or biased, it will confidently give us the wrong answer. To understand how these systems work and fail, we can zoom in and look at a simple example, our fisherman Matthew. His livelihood is determined by a single decision: should he go out fishing today? This is the hidden layer of logistic regression, and by the end of this video, you'll understand why a model claiming to be 99% accurate can confidently make the wrong decision far more often than 1% of the time, possibly even affecting your life. To understand how these models work, we need to go back out to sea with an old friend of the channel, Matthew. Now, he's already using linear regression to predict how many fish he will catch, and knows on a certain day whether to expect 10 or 30. But the issue is that while linear regression is great for predicting the amount of fish, it does a terrible job of knowing whether or not to make a yes or no decision. If he wasn't going to make a profit that day, what's even the point of going out? If Matthew tried tweaking the model to predict if he should go out fishing today, he might get an answer of 1.5, making no sense whatsoever. Because of this, he's hired a business consultant named Reggie to help find out one question: will today be profitable if he goes out fishing? He's fine if he makes any amount of profit in the day, he just wants to know whether it will be or not, a yes or no decision. The great news for Matthew is that logistic regression is very similar to the linear regression model we made last time. Linear predictions can be any number, but binary logistic regressions have to be a yes or no. And lucky for us, logistic regression actually follows the same pattern to implement it. To start, we need a properly labeled dataset to teach the model actually what makes a day worth going out for. This is because the model is going to look at consistent previous patterns. What do you think makes a day worth going out? Well, there may be a minimum temperature, a certain day of the week, or even a specific time of day which leads to more profit being made. What Matthew can do is label whether or not a certain day was profitable with a 1 or 0, a 1 for yes and a 0 for no. Our model would then need to look for these factors from the data you feed it and whether or not that day was profitable. These attributes are called features and are aspects of the ideal day. The only issue is how these are read. The temperature is pretty easy, it's already a number. But what about if it's cloudy? How does a computer recognize that? Well, each feature will need to be numerically encoded, which is just a way to quantify a value. For instance, the presence of clouds would be encoded with a 1 for clouds being present, and a 0 for no clouds being present. Similar to profitable days having a 1 and non-profitable days having a 0. After encoding, Reggie will get a datasheet full of numbers, not words. Now that we've cleaned our data, we can build the equation. We'll take our features and then each will be assigned a weight. Think of these weights as points for how relevant a feature is. If temperature really mattered, then it would have a higher weight. For example, if it had a weight of 2, then for every 1 degree increase in temperature, we will add 2 to our final score. But if it didn't matter as much, it might have a score of 0.2. Note though that even if it didn't matter as much, a large value can still have a significant impact. So Reggie can now start by defining the model's equation, and it might actually look familiar to some of you. It is the same structure as linear regression. We are multiplying each feature by their associated weight and adding them together with a base score. And this number that we'll get from this equation is the raw score for the day. A day with more fish will have a higher score, while a day with less fish will have a lower one, and it's commonly referred to as the log odds. So it seems pretty simple, right? But wait a minute, didn't we just say we needed a new equation? How is this number even useful? And how can we predict anything binary from this? While these scores can be used by Matthew to interpret whether a day is worth going out, it isn't very intuitive on its own, since a score of 2.3 doesn't tell us much, besides it's better than a score of 1. For Reggie to do anything actually useful with these scores, the algorithm needs to assign them to a probability to properly show how strong a day is. This way, a day of having a probability of 75% being profitable would be more worth going out compared to a day of 30%. However, if we tried to use these log odds directly as probabilities, Reggie would run into a pretty big issue quick. they would get a probability of 150% for incredible fishing days, or a probability of -40 for terrible ones. And since probabilities cannot exist outside of 0 to 100%, we need an additional step. And the good news is, the step's easy. We can easily translate these numbers into probabilities by using our log odds in an equation known as the sigmoid curve. On the screen, you'll see this S-shaped curve, and think of this like a squishing machine. You can input the linear equation into it, and it will condense any number, whether it's 1,000 or -20, so that it has to be between 0 and 1. For example, the 3 we put in here became 0.95. This successfully translates our log odds into a probability that Reggie can easily understand. Now that we have it, the day's final score can then be compared to a threshold, and this is how we can convert it into a binary decision. Think of it as a hard cutoff. If Reggie is worried about making profits, then they want to be relatively confident they will catch fish on a given day. They might then arbitrarily set the threshold to 70%. This 70% threshold means that even if a day had a 65% chance of being profitable, our algorithm will still assign a no to it, meaning he should not go out that day. If Matthew didn't care as much and was happy taking more of a risk, he could set it lower to 40%. You can see this visually on the screen here, where the cutoff is actually determined by this point on our S-shaped curve. Anything above will be classified as profitable, and anything below is not profitable. On the screen is the whole process for just temperature. We went from cleaning the data to building our equation, entering it into the sigmoid, and plotting it on the screen. The green and red dots on the bottom graph are actually our data, just showing if the temperature associated with the past data ended up with a profitable day or not. So let's say he got a score of 85% just from looking at temperature. He then packed all his gear and went out, but caught absolutely no fish. Where did our model go wrong? How did we know if we got unlucky and hit that 15% chance of failure, or if our entire model is flawed and wrong? To figure out if our model is actually flawed, we need to look at how Reggie trained it in the first place. Remember from before, models like this don't actually know what a profitable day looks like. They just recognize what patterns previous successful days had. For example, if most successful days had a high temperature, it would weigh that higher than colder days. We've already seen this. Similar to you learning in a classroom, you need an existing textbook and lecture notes. You also need to be tested with exams of similar material but different questions than what you've seen before. And that's what we were missing. We trained it, but we didn't test it. Teaching and training logistic regression these patterns is actually somewhat similar. What Reggie could do to increase the reliability of the model being fair is take 1,000 past days from Matthew's logbook and make a note of which were actually profitable. This dataset allows more patterns and variability to be captured than only 10 days worth of data. They then randomly split 800 of the days to train the model. This is how the weights from before were actually learned. During training, they are slightly adjusted and modified until the function is as accurate as possible. Similar to throwing a dart and getting better each throw until it lands a bullseye, in a textbook, you'll see this mathematical algorithm known as maximum likelihood estimation. But for Reggie, it's just about adjusting the model's aim to hit that bullseye. This allows the model to produce more accurate results, and is similar to reducing errors in linear regression using least squares. Both models attempt to find the best weights, just optimizing for different things in different ways. Once it has been trained and the model has learned the weights, it is ready to be used. However, if we stopped here, there is no way to know if it's accurate or not. If Matthew was impatient and tried using it right now, he might have gotten the okay to go out, even maybe a 99% chance for it to be profitable, but he would have sat there on his boat twiddling his thumbs for 8 hours. To prove it works, Reggie now needs to test it on the remaining 200 days that weren't used in training. If the model correctly predicts which days were profitable, it is working well. If it would have rejected going out when the day was actually profitable, then that would be classified as an error and indicates the model has bad performance, especially if it occurred multiple times. These errors can be plotted in a handy confusion matrix, a simple table showing correct versus incorrect predictions. I actually have a whole video on the types of errors you can encounter, and I recommend checking it out if you're interested. But essentially, if there are significant incorrect predictions, like rejecting 30 successful days from Reggie's testing data, this would indicate something is probably wrong with your model and needs to be looked at and refined. So where can the model go wrong? One way is if the days Reggie trained on didn't come from a fair and representative sample. Then the model learned the wrong things to look for, and money could be lost because of this bias. For example, if every hot day happened to have no clouds, but hot cloudy days were still profitable, the second a cloud is in the forecast, the model would say not to leave the house, even if Matthew would make more money, because it just simply doesn't know. Another example is if Matthew only fished in the morning. Our model could think you would not be able to catch fish any other time. And another way Reggie could have been wrong from the start is a concept known as overfitting. One way is essentially including every variable you can think of as a predicting variable in the model. Think of it like memorizing for an exam. You might get 100% on the next test, but only if it is the exact same. If any of the questions were different, you would get close to 0 right. The same goes for Reggie's model. If it had memorized the exact weather and temperature because you stuffed every feature you could think of in the model, instead of learning what actually predicts success, then it would fail on any day that was different, even if it was more profitable. Having hundreds of features in a dataset is often referred to as having high dimensionality, and is one of the many ways a model can be overfit and inaccurate. This is how a 99% accurate model fails. It could genuinely predict 99% of the data correct, but if it was trained on data that was biased, incomplete, or not representative of reality, then that 99% means nothing when the real world is different data than its training set. This is why it is crucial that the data is fair and representative, with the threshold being set carefully. It is also important to note that there are many other ways the data can be overfit or the model inaccurate. Remember, this exact method has been used to screen resumes, approve loans, and flag who might be at risk for a medical condition. It's important these decisions are made correct. This is also just an overview of a simple binary logistic regression model, with a simplified educational example of how it works with a fictional fishing business. In reality, you almost always have more advanced and complex models, data, situations, and tons of other ways the model can be overfit and inaccurate. All of this adds to the importance of understanding the foundations and always having a human in the loop. When the training data is representative and the threshold set carefully, these models can be an extremely useful and accurate tool. So if you were Matthew, what threshold would you set it to? Would you be risk averse with 80% or try your luck at 40%? Drop your answers in the comments down below and like and subscribe. And if you're wondering how Matthew even built the first model, check out my previous video on linear regression.